Very good morning to all of you students. Welcome to the physics class, and today in this session we will study electric potential and potential energy. It is the third chapter of your syllabus, and in this chapter we will study deeply the electric potential and potential energy. So student, the first topic is electric potential. As you know that electric potential is equal to the work done, and we can also define the electric potential, the work done by an external agent carrying a positive test charge from infinity to a point inside the electric field. It means that if we do any work from carrying a charge from infinity to a point inside the electric field, then the work done will be equal to electric potential, and it is denoted by V. The SI unit of electric potential is joule per coulomb, and it is also can be considered as volt. Now the dimension of electric potential is given as ml square t minus 3 a minus 1. Now we will study here physical interpretation of electric potential. Physical interpretation of electric potential means, as we know that if we have a heavy charge, that means the amount of charge is more, and if we have a small charge, then the potential drop is always carrying from high potential to low potential, and this shows that physical interpretation of electric potential. The next topic is potential difference. If we take 2 points and carrying a charge from A point to B point as shown in the figure, then the potential between these 2 points is known as potential difference, and it is given as VA minus VV is equal to W upon Q, where VA and VV are the potential at point A and B, and the difference between these 2 points gives the potential difference between A and B. Now the next important topic is electron volt. One electron volt, how can we define one electron volt? One electron volt is the amount of energy required to accelerate an electron in any electric field. That means if we provide the same amount of energy of the electron, then it will be accelerate in the electric field. 1 electron volt is equal to 1.6 into 10 to power minus 19 joule. So it is the unit of energy. Now the next topic is electric potential due to a point charge. In order to find electric potential due to a point charge, we have to take a diagram, and this diagram is given as at point O there is a charge plus Q, and at distance small r we have a point P where we have to find the electric potential due to a point charge. So in order to find the electric potential, we have to take a charge at infinity, and we have to carry this charge from infinity to a point P step by step. So first of all, we will find the force between two charges Q and Q naught, and it will be F is equal to 1 upon 4 pi epsilon naught K Q naught upon x square, because x is the distance between these two charges. Now we have to find the work done. So due to displace small displacement, the work done will be dW is equal to F into minus dx. Here minus dx is used because we have to do work against the electric field. Now if we want to get the total work done, then we have to integrate the small work done, and it will be W is equal to minus infinity to small r f dx is equal to minus is equal to minus q naught upon 4 pi epsilon naught k integration infinity to r 1 upon x square. Now we know that the integration of 1 upon x square will be minus 1 upon x. So it will be minus q naught upon 4 pi epsilon naught k minus 1 upon x whole infinity to r. Then after putting the values of limits, we get w is equal to 1 upon 4 pi epsilon naught k q naught upon small r. And finally we get v is equal to w upon q naught, because we have to find the potential, and we know that potential is v is equal to w upon q naught. So by putting the values, we get 1 upon 4 pi epsilon naught k q upon r. So finally the formula is v is equal to 1 upon 4 pi epsilon naught q upon r bold. This is the required expression for the potential at any point due to a point charge. Now the next topic is potential due to a group of point charges. If we have a number of charges q1, q2, q3 and so on, we can also take the charges positive or negative way, there is no problem. Then the total potential V is defined as V is equal to 1 upon 4 pi epsilon naught q1 upon r1 plus q2 upon r2 minus q3 upon r3 minus q4 upon r4. It means that we have to take as it is the value of charge with their sign. So we can also write it V is equal to 1 upon 4 pi epsilon naught sigma I is equal to 1 to n qi upon ri. Now the next topic is potential. Next topic is potential due to an electric dipole. As you know that in the earlier classes we have studied electric dipole and we know that electric dipole is an arrangement in which two charges, their magnitudes are equal but they are opposite in nature, are placed at a small distance. So with the help of electric dipole we will prove here its potential at two conditions. First, when the point is on the axis, and second, when the point is on the equatorial line. So first point is potential at a point on the axis of dipole. So take a diagram. This is an electric dipole which have a charge minus q and plus q, and O is the center, and take a point P at the center of electric dipole at distance small r. Now we have to find the electric potential at point P due to charges, because point P is at the axis of electric dipole. So first of all we will find the electric potential at point P due to plus q charge, and it will be V1 is equal to 1 upon 4 pi epsilon naught q upon r minus L. In the same way, we can find the electric potential at point P due to minus q charge, and it will be V2 is equal to minus 1 upon 4 pi epsilon naught q upon r plus L. Now, the net electric potential at point P is given as V is equal to V1 plus V2. On putting the values, we have 1 upon q upon 4 pi epsilon naught in bracket 1 upon r minus L minus 1 upon r plus L. So finally, on putting the values and by putting the value of P, P is equal to Q into 2L, we get 1 upon 4 pi epsilon naught 2QL upon r minus L square. Now we know that L square is very small in the compare of R square, then we can neglect it in the compare of R square. So finally we get the electric potential at a point P on the axis V is equal to 1 upon 4 pi epsilon naught P upon r square volt. Now the second condition is when the point is at on the equatorial line of the dipole. In this case, in this case we take a diagram here, and there is a point P which is placed on the equatorial line of electric dipole, and here we have to find the electric potential at point P due to both charges. So according to diagram, first of all we will find V1, and V1 is the electric potential due to plus Q charge. So 1 upon 4 pi epsilon naught Q upon Vp, where Vp is the distance and V2 is the electric potential due to minus Q charge. Now the net electric potential at point P will be V is equal to V1 plus V2. On putting the values, we have total electric potential at point P will be 0 because the distance is same from the corner point and on the equatorial line. Now the next topic is equipotential surface. It is also important topic, and it is a common definition of electric potential. So any surface over which the electric potential is same everywhere is called equipotential surface. You can also see from the diagram, in this diagram, the outer surface and the inner surface both have equipotential surface because at each point of these surface the potential is same at everywhere. That's why it is called equipotential surface. Our next topic is electric potential energy. The next topic is electric potential energy, and electric potential energy can be defined as the electric potential energy. The electric potential energy of a system of a charges is the work done has been done in bringing a charges from infinity to near each other to form the system. It means that electric potential energy and electric potential both are almost same. In the same case, we have to do some work done for carrying a charge from infinity to a point inside the electric field. So from the figure you can see that it is a combination. This figure is a combination of two charges Q1 and Q2 which are placed at a distance small r. So first of all we will find potential due to charge Q1. So it will be V is equal to 1 upon 4 pi epsilon naught Q1 upon r. And we have to find the work done. That means we know that work done due to Q2 charge is W is equal to Q2V, and on putting the values of V we get 1 upon 4 pi epsilon naught Q1 Q2 upon R square joule, and this work done is considered as the electropotential energy. This is the required expression for the electric potential energy. U is equal to 1 upon 4 pi epsilon naught Q1 Q2 upon R. Now we can find the potential energy due to a system of charges. If there are so many charges are take place on a system, then we can find the electric potential energy by the given formula. U is equal to 1 upon 4 pi epsilon naught Q minus Q naught upon R12 minus Q2 Q3 upon R23 and Q1 Q3 upon R13. That means we can find the electric potential energy due to the number of charges. Work done. Next topic is work done in rotating an electric dipole in an electric field. So here we can also use the concept of electric dipole, and we have to do the work done by rotating it. That means we have to use here moment of force. So from diagram, electric potential is rotated at angle theta, then the moment of force tau is equal to P sin theta, and we have to find the work done, and small work done dW is equal to force into angular displacement. That means tau into d theta, and on putting the values we get P sine theta into d theta. Now on integrating from theta 1 to theta 2, because theta 1 is the initial position and theta 2 is the final position, we get the required value W is equal to PE cos theta 1 minus cos theta 2. On putting the values of theta 1 and theta 2, we get the required work done for rotating an electric dipole in the electric field. Now student, there is some numericals which can be solved by you by using the above description and the formulas which is studied by you and us in the above chapter. So you can solve this question by the explanation. Now we will study here some most important numericals. For example, see this example, a regular hexagon of side 10 cm has a charge 5 microcoulomb at each of its vertices. Compute electric potential at the center of hexagon. So here there are number of charges which are placed at the corner of a hexagon. So first of all we have to find the potential due to first charge, and after that we will multiply it by 6 because the charges are same and the distance are also same. So we get V is equal to 6 Q upon 4 pi epsilon naught R. On putting the values, we get the required value 2.7 into 10 to the power 6 volt. So student, you can solve these questions with the help of above description and solve numerical and try to understand all the definitions and basic concept of electric potential and potential energy. Thank you very much.